Within 20 degrees of the equator, cacao survives only in constant heat, humidity, and shade. An understory tree evolved for the tropical rainforest. Cacao grows its fruit directly from the trunk, a rare trait called cauliflory, so tiny insects can pollinate flowers hidden from the canopy. Ripeness is judged by color and sound. Too early, flavor never forms. Too late, fermentation starts inside the pod. Harvesting demands precision. One careless cut damages future flowers. Every pod is removed by hand. No machine can replace this skill. Inside each pod, bitter beans sit in sweet pulp. Chocolate flavor doesn't exist yet. It must be created through fermentation. Beans are extracted immediately. Fermentation must begin within hours, or unwanted microbes permanently ruin flavor. Criollo offers rare elegance. Forastero delivers yield, and Trinitario balances both. Genetics define flavor potential before processing begins. Harvested beans move fast. Fermentation is controlled biology, heat, microbes, and time, transforming seeds into chocolate precursors. As night falls, transformation begins. In wooden boxes, biochemistry will decide whether today's harvest becomes chocolate or waste. Fermentation is where cacao becomes chocolate. In wooden boxes, microbes transform raw beans into flavor through heat and time. Fresh beans enter with sugar-rich pulp. No cultures are added. Wild microbes begin fermentation naturally within hours. Yeasts consume pulp sugars, producing alcohol, carbon dioxide, and heat, liquefying the pulp and exposing beans to oxygen. Oxygen triggers acetic bacteria. Alcohol becomes vinegar, temperatures spike, and the heat kills the bean. Workers turn the mass to control heat and oxygen. Without this, beans ferment unevenly and flavors fail. Inside the bean, enzymes create flavor precursors as bitterness fades and color shifts from purple to brown. Temperature and pH curves guide fermentation. Deviations signal contamination, poor aeration, or lost flavor potential. The cut test reveals success: uniform brown color, correct texture, clean acidity, and no purple streaks. After 6 days, pulp is gone. Fermented beans must dry immediately or flavor deteriorates. Drying locks in fermentation chemistry. Over 2 weeks, bitter seeds become chocolate's foundation. Solar drying demands precision. Beans dry from 60% moisture to exactly 7. No higher, no lower. Beans are spread 2 inches deep. Too thick traps moisture. Too thin seals moisture inside. Moisture evaporates slowly. Surface water leaves first, then internal moisture migrates outward as flavor refines. Rain can destroy a harvest. Even minutes of moisture can restart microbes and cause mold. Drying ends at 7% moisture. Uniformity matters. Every bean must fall within range. Workers remove defects by hand. One moldy bean can contaminate an entire shipment. Beans are packed into 70-kilogram jute sacks, breathable, traceable, and ready for export. Containers hold 21 tons of beans. Airflow and moisture control protect flavor during transit. At sea, heat and condensation test drying quality. There are no corrections mid-voyage. Dried beans arrive intact, holding only potential. Roasting will finally unlock chocolate flavor. Before roasting, beans must be cleaned. Stones, metal, and debris threaten both safety and equipment. Screens and airflow separate beans by size and density, removing stones and broken fragments. Powerful magnets extract metal fragments invisible to the eye, but disastrous for grinding machinery. Roasting transforms chemistry into flavor. Heat drives hundreds of reactions that define chocolate aroma. Controlled heat triggers Maillard reactions. Too cool, flavor stalls. Too hot, bitterness dominates. Digital controls guide precise temperature curves. Flavor is shaped second by second. Light roasts preserve fruit. Medium builds classic chocolate. Dark emphasizes roasted intensity. Rapid cooling halts roasting instantly. Any delay pushes flavor past its target. Roasting dries shells until brittle, allowing clean separation from the cacao nib. Roasted beans move to cracking. Shells will be removed, leaving pure cacao nibs. Cracking and winnowing separate flavor from waste, using physics to isolate pure cacao nibs. Impact mills shatter roasted beans, breaking brittle shells and fracturing dense nibs. The result is controlled chaos. Shell, nibs, and dust mix together, awaiting separation. Airflow lifts light shells upward while dense nibs fall. Separation by physics, not touch. Shells are removed completely. In chocolate, even small shell remnants cause bitterness. Screens refine nib size. Oversized pieces return for recracking until specifications are met. Finished nibs must contain almost no shell. Purity determines texture and flavor. Pure cacao nibs, rich in cocoa butter, flavor compounds, and chocolate's natural stimulants. Nibs are stored cool and dry, separated by origin for precise flavor blending. Next comes grinding, where solid nibs liquefy, becoming chocolate for the first time. Grinding uses friction alone, melting cocoa butter and turning solid nibs into liquid chocolate. Pre-grinding reduces nibs to fine particles, preparing them for full liquefaction. Granite stones crush particles slowly, releasing cocoa butter and creating smooth liquor. Grinding ruptures cells, releasing cocoa butter that coats particles and enables flow. Ball mills refine faster, using impacts and shear to reach smooth texture in hours. Below 20 microns, chocolate feels smooth. Above 30, grittiness appears. Grinding temperatures must stay hot enough to flow, cool enough to preserve flavor. Chocolate liquor flows, pure cacao, fully ground, the base of every chocolate product. High fat content gives chocolate liqueur its thick, glossy flow behavior. Stored warm, liquor moves onward to pressing, conching, or final chocolate. Pressing splits chocolate liquor into cocoa butter and cocoa solids using immense pressure. Hot chocolate liquor is pumped into press pots, ready for fat extraction. Hydraulic rams apply extreme pressure, forcing cocoa butter out of the solid mass. Golden cocoa butter flows out, pure fat that melts just below body temperature. What remains is press cake, dense cocoa solids with minimal remaining fat. Alkalization raises pH, darkening color and softening cocoa's natural acidity. Different Dutching levels create cocoa powders ranging from light brown to black. Press cakes are milled into fine cocoa powder, sized for specific uses. Fat content, pH, color, and particle size determine cocoa powder quality. Cocoa powder ships worldwide, while cocoa butter feeds chocolate, cosmetics, and pharmaceuticals. Chocolate formulation blends liquor, sugar, milk powder, and cocoa butter to create smooth, balanced chocolate ready for conching. Automated scales ensure each ingredient is added with extreme precision. Small deviations can ruin flavor, texture, or tempering behavior. Sugar is pre-refined to below 30 microns to prevent grittiness, ensuring chocolate feels silky on the tongue. High shear mixing coats sugar and cocoa particles with fat, forming a coarse paste ready for conching. Longitudinal conches reduce particle size, evaporate volatiles, and develop flavor over 12 to 72 hours of continuous shearing. Conching gradually reduces particles from 80 microns to below 20 microns, creating perfectly smooth chocolate. Heat and agitation remove moisture and volatile acids, mellowing sharp flavors and improving chocolate's aroma and balance. Rotary conches mix chocolate in 3 dimensions, achieving smooth texture in half the time of traditional longitudinal machines. Lecithin reduces viscosity, allowing chocolate particles to slide past each other, making chocolate fluid without extra cocoa butter. Conch's chocolate flows smooth and glossy, perfectly refined, ready for tempering to achieve snap, shine, and ideal texture. Tempering controls cocoa butter crystals, determining chocolate's shine, snap, and stability. Same chocolate, different crystal structure. Tempered chocolate shines, snaps, and melts correctly. Precise heating, cooling, and reheating guide cocoa butter into its ideal crystal form. Continuous tempering machines automate crystallization, producing perfectly tempered chocolate every minute. At the right temperature, stable cocoa butter crystals form and multiply. Seating introduces stable crystals directly, guiding liquid chocolate into proper temper. Gloss, snap, and setting speed confirm whether chocolate is properly tempered. Tempered chocolate contracts as it sets, releasing cleanly from molds. Improper temper causes fat bloom, white streaks from unstable crystals rearranging over time. Tempered chocolate moves quickly to molding before crystallization thickens it. The molding line transforms tempered chocolate into finished bars through precise, fully automated choreography. Clean, preheated molds prevent defects and protect chocolate's delicate crystal structure. Servo-controlled depositors fill each mold with exact weight and perfect flow, Vibration releases trapped air, creating flawless surfaces and uniform structure. Controlled cooling solidifies chocolate while preserving its ideal crystal form. As chocolate cools, it contracts slightly, pulling cleanly from the mold. Perfectly crystallized bars release instantly, glossy, intact, and ready for inspection. Snap and surface gloss confirm correct temper and premium quality. Every bar is scanned for safety and verified for exact weight. From cacao pod to finished bar, science, precision, and craft complete the journey.